My name is Joseph Moon and this is Physics 2211 Lab 3 Black Hole. So the sections I will cover are Introduction, Models, Code, Results, Discussion, and Conclusions. For the introduction, there are two parts to this lab. Part 1, the purpose is to determine the mass of a black hole using the motion of an orbiting star. The system is the star and the surrounding is the black hole. We have initial conditions where we know the star's mass and it is orbiting a black hole. And then for the preview, we found that the mass of the black hole is 1.23764 e34 kilograms. For part 2, the purpose is to determine the initial velocity of spaceship to get it close enough to the black hole from part 1 while still being able to leave the system. So to find the net force in this situation, we would need the gravitational forces with two different systems, one system being the planet and another system being the spaceship. The initial condition is the planet is orbiting a black hole and the spaceship is on the planet. And then the preview of the results is the ship's initial velocity is negative 3.95 e7, 2.0 e6, 0 meters per second. The models we will need are Newton's second law and gravitational force. So for Newton's second law, we can see that it is net force is equal to change of momentum over change in time, and then when this change is infinitesimally small, we can say that it is equal to d dt. So d dt of momentum, we know that the vector can be expressed as the magnitude times its direction, and then when we further break this down into its parallel and perpendicular components, we have the equation below. For gravitational force, it is a fundamental force, non-constant force, and is an attractive force between two objects. So using the gravitational force equation, we can derive to solve for the mass of the black hole. So the code for part 1, we have the initial conditions, and then we calculate for the star's velocity. And then here we have the initial and final velocities, initial and final momentum. We find dp dt, and then plug in dp dt is equal to f net, and then find dp dt parallel and perpendicular components, and then find the mass of the black hole. So for the results, we can see that the f net perpendicular is equal to this number, f net parallel is equal to this number, and then f net is equal to 8.94183 e28 newtons. And then the answer for the mass of the black hole is 1.23764 e34 kilograms. So we can see the star orbiting the black hole, where the pink arrow is the perpendicular, orange arrow is the net force, and then the cyan is the parallel component of the net force. So for the code for part 2, we have the mass of the black hole in constants, planet's initial velocity, and then the ship's initial velocity, which is calculated using trial and error. And then we can calculate the gravitational force of the surroundings on the planet, and then when the ship is the system. And then we would solve for the net force using these four forces, and then do position iteration. So for the results of part 2, we can see that the initial velocity of the ship is found to be negative 3.95 e7, 2.0 e6, 0 meters per second. So some sources of error include accuracy, because trial and error was used to find the initial velocity to where the spaceship will leave the orbit and not get sucked into the black hole. So some other values may be more accurate than these initial velocity values. And then for approximation, this lab used a simulation which does not account for certain external forces and factors that will be in play. Our conclusion, we have how is the net force and its components different from the rate of change in momentum and its components. So these two are the same values mathematically, but they are easy to solve for rate of change in momentum and its components rather than the values of net force. And this is because F net is equal to the sum of forces on the system, while the change of momentum over change in time is just mv minus mv initial. And so you just need to solve for the velocity for the change of momentum over change in time. And then what initial velocity would the spaceship need to have to enter some orbit around the black hole? And so this velocity is found below, and these values were obtained by also some trial and error, but the same formula for the planet's speed was used to find the ship's speed.